Hello and welcome to our lesson on rotational symmetry. In this lesson, we'll delve into this concept, which involves rotating a shape around a center point and observing its properties. Our primary focus will be on understanding how a shape can look the same after a certain amount of rotation. First, we'll start by defining rotational symmetry and the key terminology associated with it. Next, we'll discuss how to determine the order of rotational symmetry for various shapes. Finally, we'll apply this new knowledge through several examples to ensure we can recognize and use rotational symmetry in different contexts. In our previous lessons, we have established a solid foundation by discussing 2D shapes and the center of rotation. We have understood the characteristics and properties of two-dimensional figures. We also now know that the center of rotation is the fixed point around which a shape is rotated. Building on this foundation, we can now introduce the concept of rotational symmetry. With this new understanding, you'll be better equipped to tackle more advanced geometric problems and appreciate the symmetrical properties of shapes. Let's get started and explore the world of rotational symmetry. So what is rotational symmetry? A shape has rotational symmetry if it looks exactly the same after being rotated around its center by a certain angle. The center of a shape is the fixed point around which the rotation occurs. Let's develop this with an example. Here we have a simple square plotted at the highlighted points. Let's see what happens when we rotate this square 90 degrees around its center. Notice how it looks the same before the rotation. Let's now rotate it another 90 degrees to give a total rotation of 180 degrees. Again, it looks exactly the same as before. Can you guess what happens if we rotate it another 90 degrees to give a total rotation of 270 degrees? Yep, it still retains its original position. And you guessed it, rotating it a further 90 degrees has the same effect. This demonstrates that a square has rotational symmetry at the angles 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Let's introduce some new terminology to describe this insight. We have order of rotational symmetry. This is the number of times a shape looks identical when rotated a full 360 degrees. The rotation of 0 degrees is always counted as 1. For example, for the square, as mentioned, it looks identical when rotated 0 degrees, which is its original position, 90 degrees, 180 degrees, and 270 degrees. We don't count 360 degrees since it is a full rotation and therefore the same as 0 degrees. Thus, a square has an order of rotational symmetry of 4, as it can be turned at 4 different angles and look the same. For some shapes, it's intuitive how many rotational symmetries they have. A square, for example, has an order of rotational symmetry of 4. You might also be able to visualize how an equilateral triangle has an order of rotational symmetry of 3, at 0 degrees, 120 degrees, and 240 degrees. For other shapes, where it's not immediately clear, we return to our method involving tracing paper. Let's apply this to a regular pentagon. We begin by placing tracing paper over the shape and marking the center of rotation. Next, we rotate the tracing paper slowly while keeping the center fixed. We mark which angles the shape looks the same as its initial position. We then count how many times this happens over a full rotation, which is 360 degrees. With our regular pentagon example, we can see it has an order of rotational symmetry of 5. A final thing to note is that even if a shape only aligns with its original position at 0 degrees, it still possesses rotational symmetry. This is termed an order of 1. Every shape has at least this minimal rotational symmetry. So, how do our findings from today's lesson generalize? We saw that an equilateral triangle, which is a regular three-sided polygon, has rotational symmetry of order 3. We then saw that a square, which is a regular four-sided polygon, has rotational symmetry of order 4. Finally, we saw that a regular pentagon, which is a 5-sided regular polygon, has rotational symmetry of order 5. We can see a pattern developing here, and this continues for all regular polygons. So a regular n-sided polygon has rotational symmetry of order n. This means that an octagon, which is a regular 8-sided polygon, has rotational symmetry of order 8. Another interesting result is that circles have a rotational symmetry of infinite order, since a rotation of any angle about their center leaves them unchanged. In today's lesson, we explored the fascinating concept of rotational symmetry within geometry. We began by defining rotational symmetry, understanding how a shape can look identical after being rotated around its center by a specific angle. We then delved into the idea of the order of rotational symmetry, which counts how many times a shape appears the same during a full 360-degree rotation. We also highlighted that every shape has at least a minimal rotational symmetry of order 1, even if it only aligns with its original position at 0 degrees. By recognizing the order of the rotational symmetry of a shape, we can more effectively solve geometric problems.